So yeah, I guess these lectures were born out of a perception that there's maybe some frustration at not being able to understand climate simply, simply from first principles. That the only things that we can use are climate models and are hard to understand. And the decision to do this was really born out of conversations with Rob Sokolow and Stefan, especially Mike Celia, who said, it feels like unless we turn to models, we can't understand anything. What can we understand on the blackboard? And I said, well, I think there are some things we can understand. Climate modelers have simple models that they use to understand their simulations, but they haven't really been pulled together and condensed in a way that's accessible for people outside the field. So that's what we're trying to do here. So in addition to these lectures, I wrote up some notes. And so those are available. So those are available on the archive, which is an internet preprint repository. So here's the URL, and if you Google archive and my last name, you'll find it. And these notes include more details and footnotes and references, and so sometimes I'll refer to these for. All right. So let's start with just a zeroth order climate model. So if we're going to try and understand the Earth's climate, and in particular the surface temperature of the Earth, what are the minimum ingredients we would need? All right, so as most of you probably have seen at some point before, one of the ingredients we need is the energy balance of the planet. Right? There's a certain amount of energy coming in, and it has to be balanced by energy going out. So we've got sunlight coming in, and this is globally averaged and including reflection by ice and clouds and things like that. So it's a globally averaged net incoming solar radiation. So this is incoming sunlight. This has a magnitude of about 240 watts per meter squared. So this has to equal the outgoing, what we call the thermal radiation that Earth emits to space. Right? Everything that's warm that has any temperature emits thermal radiation. A simple formula for that is something that you may have seen in undergraduate physics. It's a constant times the temperature to the fourth, and this is the emission temperature. And you can think of this as sort of an effective temperature at which the Earth is radiating. And so this is sometimes known as the outgoing long wave. Long wave just means that it's basically in the infrared, that our eyes can't perceive it. Outgoing long wave radiation, abbreviated OLR. And so this constant is known, and so you can solve for this emission temperature. This is a number people may have seen before. It gives you about 255 kelvins. That's about minus 18 Celsius. So clearly that's not the surface temperature of the Earth, right? It's too cold. So this is significantly less than the observed surface temperature, which is about 288 Kelvin, or 15 Celsius. Right? This is the observed value. Now this makes sense because this outgoing long wave radiation isn't emitted by the surface of the Earth. It's emitted by the greenhouse gases in the atmosphere. Right? A greenhouse gas, by definition, is one that just absorbs and emits this thermal infrared radiation. And indeed, this is a typical temperature for the atmosphere. So that makes sense. But we're interested in surface temperature. That's kind of the central variable, the most important variable in climate science. So this gives us a sort of characteristic atmospheric temperature, but how do we relate this to the surface temperature? So that's the first question that we want to answer. In a first order quantitative way. We're not going to get the exact right answer, but we want a simple model that'll get us in the ballpark. All right. For that, we need to understand a little bit more about how the atmosphere works. So here's the picture. Space here. So the pieces that we'll need here are an ocean. Can people see if I write down here?
Yep.
And above the ocean, there's this layer of atmosphere about 1 kilometer deep that's in close contact with the surface and feels the effects of the surface on short time scales. We call that the boundary layer, and I'll abbreviate that with BL. And actually, I think I want to try this as a solid line. So the boundary layer is just the lowest part of the atmosphere, about 1 kilometer deep. Then we have the rest of the atmosphere, and then up here is space. All right, so of course we've got the sun. And by the way, I should say here that our simplified model for the Earth is that first we're gonna consider the tropics. The tropics takes up about half the area of the Earth's surface, and it's where most of the radiation from the sun is coming in. It's where most of the infrared radiation is going out. So we should take it as a proxy for the whole Earth, to first order. The other thing we do is, since the tropics is mostly ocean, we just idealize the surface as being all ocean. So this sort of tropical atmosphere above a tropical ocean is a stand-in for the whole thing. All right, so the sunlight's coming in, and it's all being absorbed in the ocean. So now, in a steady state, the ocean has to get rid of this energy, right? So now you might think that it'll just warm up and it'll emit thermal radiation, and that's how it'll get rid of this incoming sunlight. And indeed, it does this, right? You can measure a lot of upwelling thermal radiation near the surface. But we have these greenhouse gases, right? And by definition, they absorb and emit thermal infrared radiation. And they're very effective at doing this lower down in the atmosphere where their concentration, especially water vapor, is very high. So we have our water vapor molecules, which I'm going to draw with a sort of Mickey Mouse-like cartoon. We've also got carbon dioxide, whose chemical configuration is linear. So we've got these greenhouse gas molecules absorbing the upwelling and emitting downwelling, and these guys basically cancel out to first order. So this is visible, this is sunlight, but this is in the infrared, IR. Right? So the planet, the ocean surface can't cool by radiation because of the greenhouse gases. It has to find another way to cool off, to get rid of all this energy it's absorbing from the sun. What does it do? It does the same thing we do. It sweats, it evaporates, right? Evaporative cooling is the key. And so the ocean is going to evaporate water molecules. So I've got the water molecule here again, but now in a different capacity, not in a radiative capacity, but in more of a pure thermodynamic capacity. So the ocean is cooling by evaporating. It evaporates into the boundary layer. It also warms up the boundary layer a little bit because the ocean surface is maybe 1 degree warmer than the air in the boundary layer. So you've got this ocean moistening and warming this air. But then this warm, moist air is going to start to convect. It's going to start to rise. Right? But as this air rises, it's going up to lower pressures. When you lower the pressure on an air parcel, it cools, right, as it expands. You guys know that from letting the air out of your bike tire, right? The air that comes out is cold because it's expanding. But moist air that cools is going to condense. It's going to make clouds and precipitation. So these water molecules are coming together, and I'm going to try and draw a raindrop here. That's raindrop. And these raindrops are more than incidental. Why? This is actually a surprising thing that if you don't study the atmosphere as an atmospheric scientist, you might never appreciate this. But rain plays a key role in the energy cycle of the atmosphere. Why? Because the heat that the ocean lost when the water evaporated, the heat that the ocean had to put in to get the water to evaporate, the same heat that you put in when you might boil water off of a pan, that latent heat that's in the water you get back when the water condenses. So every time a raindrop condenses and falls to Earth, it's heating the atmosphere, right? And that heat actually came from the sun. So each raindrop is basically concentrated sunshine, right? And water vapor is the conduit by which that sunshine gets concentrated and then lofted to the upper atmosphere. And once it's up here, so this raindrop formation is heating the atmosphere, so I'm just going to draw squiggly lines here just to represent that it's heating the atmosphere. And once you're up this high, now there's not that many greenhouse gases above you getting in the way. So once this heat is transported aloft, now you can radiate it back to space in the infrared. And that's how the energy cycle of the atmosphere works. So you see, there's really sort of two distinct processes, which I've intentionally split in two sides of this diagram. And let's see if you'll permit. Oh, yeah. So on this side, we have radiative processes on the left. And on the right hand, we have convective processes. And so we describe this state as one of radiative-convective equilibrium. And we'll abbreviate it as RCE, radiative-convective equilibrium. So this is our paradigm for energy flow in Earth's atmosphere. All right. So now knowing that, we want to go back and answer this question. So what does understanding radiative-convective equilibrium do for us? Well, now, let's consider one of these convecting parcels. And now we'll use some sort of intro-level thermodynamics to try and get at this relationship. So, what's this thermodynamics? Let's take the first law of thermodynamics. So the heat into or out of a parcel of air looks like that. So hopefully that's familiar. All right, so Q is the heat in or out, U is the parcel's internal energy, P is the pressure, V is the volume. And by the way, I'm assuming that the mass of the parcel, m, which is just the density times the volume, is conserved. All right, so we've got the first law, and then we have an ideal gas. We have a couple more equations we can write down. So we can say that the total energy is the mass times the specific heat at constant volume. And we also have the ideal gas law. And I'll write the ideal gas law this way as the pressure equal to the density times the gas constant. So this is a gas constant for air. Really for dry air, and in later lectures, we'll need a gas constant for water vapor times the temperature. All right. So if we, and so the details of this are in the notes, but if we,
Can I ask a question?
question, please.
You said gravitational energy irrelevant?
So
I mean, somebody's got to lift the water up.
that's right. So the way to say that is, so for, this is the internal energy.
Yeah,
It's
yeah,
just the internal energy.
Yeah, sure. Well, what happens to the gravitation?
So gravitation is going to come in through P and hydrostatic balance. I'll write that down in a second. All right. So if you plug these guys in and do a little bit of rearranging, you get this. The CP is just the gas constant plus CV. And these guys have units of joules per kilogram per pound. All right. So now we add two more ingredients. We assume that when this parcel is rising, that there's no heat exchange with the environment. So it's rising, it's expanding, things are happening, but it's not gaining or losing heat to the environment. So we say that it's adiabatic. So that means that dq equals 0. And we also assume that pressures are hydrostatic, which means that the change in pressure as it rises is just equal. If it rises a certain distance dz, then the change in pressure is just the weight of the air in between the two levels. And this is one place where gravity enters this whole thing. So now, if I take this equation, dq equals 0, I can, this is 1. I'll substitute this in here. The rows will actually cancel. And what you'll find is a quantity called the dry lapse rate, and it's defined to be minus dt dz. So how fast is the partial's temperature declining as it goes up, right? This is just the cooling with expansion and rise that we were talking about. And what you find is that the rows cancel, so the g is left, the cp is left. So that's all it is. It's g over cp, c sub p. So you can plug in numbers. So g roughly 10 meters per second squared. Cp is about 1,000 joule per kilogram Kelvin. And this gives you about 10 Kelvin per kilometer. So we call this the dry lapse rate. So this is telling you, if your parcel had no moisture in it, how fast would it cool as it rises? That's what it's telling you. And you get it just from sophomore level thermodynamics. Right? And if you go outside, pretty much most places over the Earth, certainly during the day, and you measured how fast the temperature was decreasing with height, you find a number more or less like this, especially close to the surface. Right? All right, but there's nothing in here about moisture. And I said that as this parcel rises, it cools, but then it condenses water, and that water releases latent heat. So you have to take that into account. So I won't go through the details here. You can do an analogous calculation, which you have to include an additional term for water vapor. Makes things a little more complicated. The calculation is done in the notes. What you find is you get a moist lapse rate. So instead of gamma d, it's gamma m. Instead of being constant with height, it turns out to vary a bit with height. Not by orders of magnitude, though. Near the surface, it might be something like 4 Kelvin per kilometer. And then as you get higher up, well, most of the water vapor is gone, and it behaves just like a dry parcel. So high up in the atmosphere, it's close to this 10 Kelvin per kilometer value. So it varies a bit, not a ton. So what we'll do, in terms of trying to build a simple quantitative model of RCE, is we'll just take an average. So we'll let gamma m bar be 7 Kelvin per kilometer. And that'll just be an average typical value that we use. All right. So this is telling us how a moist parcel, how its temperature changes as it rises throughout the atmosphere. But it turns out that the temperature of this convecting parcel is the temperature of the tropical atmosphere, right? If the radiative cooling coming from here cools the atmosphere much lower than temperatures consistent with this, then convection will just start to pop up, and it'll kind of adjust the atmospheric temperature profile back to roughly that value. So even though I just did a calculation for a convecting parcel, it turns out to really describe the whole atmosphere. So that means, but this is dt dz, right? So this is telling me that my atmospheric temperatures as a function of z, this lowercase a is just for the atmospheric temperatures. This should just be my surface temperature minus this guy times z, because this is just dt dz, right? It's just telling you the rate which the temperatures are decreasing.
Excuse me?
Yes.
Hi, back
Yes.
here. Just a quick question before you proceed.
Yes.
In the notes, you mention a point here that says that using the hydrostatic balance is somehow a little fishy because this is not actually a static atmosphere. By definition, it is dynamic and convecting. Is there a way to establish why that is a good enough approximation to use in this calculation?
So you can take into account that you can take into non-hydrostatic effects into account here, but they only give corrections. So the atmosphere, as we'll see, is maybe about 15 kilometers deep. And if you try to apply this equation for much larger distances, then it doesn't make sense, right? Because in fact, if I take z going to infinity, then I get a negative number, right? So clearly there's some approximation going on here. But as long as we stay in the bottom 10, 15 kilometers of the atmosphere, this is a very good approximation to the sort of full expression that takes into account non-hydrostatic.
Is it easy to derive that bound, or is that more of an observed reality?
No, it's not hard to derive. I mean, Oh, I won't do it here.
Okay.
But if it's not in the notes, I think there's a reference in the notes that does it. Yeah, and it's simple. It can be done. It can be done on a blackboard. So, yep. Good. Any other questions? And this is a really important picture. So I hope this energy flow of the atmosphere, that it kind of comes in through radiation, gets converted into the latent heat of water vapor, and water brings that up, transports that heat to the upper atmosphere, where it is then free to radiate away. That's key. Very good. Okay, so now we know how atmospheric temperatures are related to surface temperatures, right? Well, we somehow have to connect this with the emission temperature. But the emission temperature is, it's an average temperature of the atmosphere. So if I think of, so if TEM is kind of an average atmospheric temperature, well then, the sort of simplest thing to do is to assume that this occurs halfway through the atmosphere. So I know, so this occurs at an emission pressure, which is just 1/2 of an atmosphere. Right? So I assume this is an average atmospheric temperature. I assume it occurs at an average atmospheric pressure, halfway up in pressure coordinates. So there's a quick calculation you can do. I'll skip it here. It just involves hydrostatic balance. It's simple. It's in the notes. What you find is that the height at about 1/2 an atmosphere, and this, the height at 1/2 an atmosphere is about 5 kilometers. Okay? Well, now I'm good to go. So now, I just rearrange this, and I say at the surface temperature, so what I'm going to do is I'm going to evaluate this equation at this emission height, right, where I should have the emission temperature. So Ts equals T emission plus gamma m bar, the average lapse rate, times Z emission. Right? Evaluating this at the emission height and rearranging a little bit. Now let's plug in some numbers. What do we get? By the way, I never did this calculation before preparing for this lecture. This is not the model that's in the textbooks. I have not seen a single, I mean, I didn't invent this. There are other people who kind of know this. But in terms of this being in a textbook, I haven't seen it. And so preparing these lectures, I was like, well, what's the simplest model we could do? And then I wrote this down, and you'll see. So what do we get? So this is 255 Kelvin plus 7 Kelvin per kilometers plus 5 kilometers. 7 times 5 is 35 plus 255, it's 290. It's not bad. That's the observed value. So this is essentially, 2, maybe 3 equations that gets you in the ballpark, and it does it for the right reason. Right? There's other books that write down even simpler models. They get the wrong answer, and then they introduce some fudge factor, some emissivity for the atmosphere, some tunable parameter. They say, oh, if I set this parameter equal to 3/4, then I get the right answer. Right? It's not for the right reason. All right. So this is sort of part 1 of this lecture, and we're right on time, which is good. So this is our zero-order picture of the atmosphere. It gives a surface temperature. And so for the second part of the lecture, I want to talk about, well, really what the lecture was entitled, global warming. How does this change, and what are the time scales on which it changes? Warming fast and slow. So any questions on this before we move on to that? Yes, Dan.
So you make a bunch of approximations, like if TM is average.
Yep.
So are those good?
Yes.
Yeah. but that's something that you need to do a lot more work to check.
Exactly, that's right. So basically, what I'm doing here is, and this is, so in the notes, you give references and you say, why is this reasonable, and there's lots of caveats. And I posted these notes online, and then the first feedback I got was, there are too many footnotes in this. And I thought, are there too many footnotes? But I thought, how else do you do it, right? If you're going to present something simplified, people are going to have questions, and you have to have some answers or references to the many, many questions you could ask, right? Because I made approximations all over the place here. But what I'm trying to do is give you, from someone who studies this, their best sense, right? Everything that's on the board here, is sort of consistent with, I guess, the things that I have seen and have read, both in my reading other papers and in my own research. So I don't think anything here is a lie.
I have a question.
Yes, please.
So the things the image set you just mentioned, it's a black body or something?
Yeah, you assume a black body, or you assume a gray body, right? That it absorbs at all frequencies, but maybe it's not totally opaque. Maybe it can, lets a certain amount of light through. And that is true for the atmosphere, but to first order, I think the best approximation is to think of it as a black body, right? Because there's maybe something like 1/6 of the radiation that's emitted at the surface. No, it's even less than that. It's about 10% of the radiation emitted at the surface actually makes it all the way to the top.
But the atmosphere, it's not, it depends on the greenhouse gas density.
That's absolutely true. So I'm ignoring all that here, and then tomorrow's lecture we'll take those ideas here. Yeah, Mike.
How should I think about the fact that you have ocean everywhere? Should I be thinking about land in some different way, or how does that come into the story?
Good. So the main reason I did that is because I wanted you to think about the surface cooling mainly by evaporation. And if you're moisture limited, then it gets more complicated. It turns out that the ocean temperatures, because there's so much more ocean than land, especially in the tropics, that what's happening in the ocean dominates the climate. And so convection warms the atmosphere here, and then this air either blows over the land or directly communicates this heating to the land surfaces. Now, land temperatures themselves can vary a lot, right? If you're somewhere that's very dry, the surface temperatures are higher because you are indeed moisture limited. But if you want to think about what sets the temperature of the Earth's oceans and also the upper atmosphere everywhere, then I think this is a good start. Yeah, Gabe.
So, I mean, one thing that is often neglected in these simple models is absorption of shortwave by the atmosphere.
Yes.
And that's a term that globally is as large
It is.
as convective heating.
Yes, correct.
Does it matter?
Not for this. It'll
Because it's
matter.
not in it, but does it?
No, but it doesn't matter for this.
Okay.
So it does matter. In all these lectures, I'm going to ignore the fact that water vapor actually absorbs a significant amount of sunlight. It's not sunlight you can see, right? It's near infrared sunlight. It's below the red part of the spectrum, but it's sort of not part of thermal radiation, at least not at temperatures, terrestrial temperatures. That's what makes light bulbs so efficient, right? Is that, like just regular incandescent bulbs, is that you see some visible light, but most of the light that's being emitted from a light bulb is in the near infrared. So you can't see it, but there's a lot of energy being pumped out there. So water vapor absorbs a significant amount of that near infrared light. The reason it doesn't matter here is because it doesn't change this fact, right? That this cancellation, even if these numbers were larger or smaller, they still cancel out. And so you might change how big this arrow is, but the atmosphere and the surface are so tightly coupled, right? Let's see. So if there were no shortwave absorption in the atmosphere, you'd have more sunlight hitting here. That's right.
So I guess the shortwave that's not absorbed by the ocean is absorbed by the atmosphere, so the water doesn't have to bring it up.
Exactly.
So it's absorbed by the water in situ.
That's right.
All right. Then,
Yeah.
second question, what about the meridional sort of inhomogeneity of this planet, right? So most of the emission to space, the net emission to space happens at high latitudes. Most of the convection happens at low latitudes.
That's right.
And so you have the transport there that
Yep.
is, I mean,
I'm ignoring it.
yeah, I know, but the Earth is not a point in a very clear way, right?
Uh-huh.
Right. I don't know if
I mean, I guess the one thing you could say is so you can do a calculation when you don't allow the atmosphere to transport heat from the tropics to the poles, and you get a somewhat different distribution of temperatures. And you might ask, if you average that, does it give you something very different? And I actually haven't seen that calculation done. Right? You get warmer tropics, you get colder poles. Is the average significantly different? I actually don't know. So that's actually an excellent question. So maybe I'm lying in that regard, right? That I'm ignoring the inhomogeneity of the Earth's surface. My guess is that it can't be too far off, maybe plus minus 5 Kelvin. But I haven't done that calculation. So A good caveat. Right, now the questions are coming. I'll take a couple more and then we'll go on and we can take
Yeah,
it.
if we replace the ocean with land and use a dry lapse rate
Uh-huh.
10 Kelvin per kilometer,
Yeah.
with the 7 you use,
Yeah.
and we can predict like the temperature, surface temperature, like 15 Kelvin warmer
Uh-huh.
than ocean.
Uh-huh.
Can we say that if the land surface kind of 15 kilometer warmer than the ocean surface?
Oh, you mean like if we look at land surfaces now?
Yeah, can we say that we can use this model to predict the surface temperature with ocean?
So not quite like that. It's a little more complicated because it turns out that this part of the atmosphere is the same over ocean and land, the first approximation, but this part is different. Boundary layer. But it turns out, so you can't just say that, oh, if I just average over land, it's going to look 15 kelvins warmer, because it's not like it's a dry adiabat all the way, because the temperature structure of the atmosphere over land is influenced by the temperature structure of the ocean. But it turns out that if you do a simple experiment where you say you warm the ocean temperatures by 4 Kelvin, the land warms a little bit more than that, and you can understand it via basically the difference between a dry and a moist adiabat. So that difference is important, but you can't apply it in quite as simple a fashion as you're describing. Jane?
I guess I'll still ask this, but I'm wondering why sensible heat fluxes aren't part of this picture. Is it because there's so much?
They're just small.
They're small. So because the.
So what Jane's
But
asking
not
about, she's
linear.
asking about the fact that the ocean, as I said, the ocean does directly just warm up some parcels in addition to moistening them. And she's asking, where is that in the energy budget? And it turns out to be almost an order of magnitude, or a factor of 5 smaller than the vapor force. All right, one last question. Yeah.
Can you say something, using this model, something relevant about what happens if you just add a little more CO2?
No, this model is very bad
Okay.
for understanding radiative forcing. So we'll need other models for that. I'm going to keep going, and we'll take it to the end. I just want to get to the end, and I don't want to keep people super late. Sorry, David. You already had like 2 questions. Don't get greedy. Okay, so let's go here. So what I want to do now is I want to build. So you guys may have heard about, committed warming versus the warming that we're seeing now, or the transient climate response versus the equilibrium climate sensitivity. So what I want to do is build a simple model that explains what those things are and allows us to put some numbers to it. So that's what we're going to do. So this is this warming fast and slow. This is a 2-box model for the ocean. So so what do we got here? So now I'm basically going to take this, just the ocean, expand it into 2 pieces. So this top part I'll call the mixed layer. And then the part below, we'll refer to as the deep ocean. And this mixed layer is the part, you can think of it as the part that absorbs sunlight and radiates radiation. And the deep ocean just doesn't see the atmosphere at all, or the sun at all. It's sort of analogous to the atmospheric boundary layer. It's the part that's sensitive to what's on the other side. Right? All right. So now I want to ask, so how does this RCE system respond to forcing? And by forcing, I mean a change, a disturbance to this energy balance at the top of the atmosphere. And what CO2 is doing is it's reducing this. If you really insisted on understanding that in this model, you could think of it as changing this height, raising it up a little bit. And if you raise it up, you'd reduce the emission temperature, you'd reduce this, you'd be out of balance, you'd be getting more sunlight than outgoing long-wave radiation. And that's what we call a forcing. So I'll draw that as a downward arrow. So let's just think, a thing that we often do in climate science is consider the forcing from a doubling of CO2. So if I just took my atmosphere in steady state, now all of a sudden I flipped a switch, I doubled the amount of CO2, all of a sudden there's a certain amount of, there's an energy imbalance with more energy coming in than going out, right? If you double CO2, this is to the tune of about 3.5 watts per meter squared. So it's the forcing from CO2. So how does the system respond? So we're considering perturbations here to a steady state climate. So I'm going to get some temperature perturbation. I denote the perturbation with a prime, right? So it's perturbation to some equilibrium temperature. So that's in the mixed layer. I have some perturbation at depth, right? It's because there's an energy imbalance, and it's the mixed layer that feels it, right? By definition, right? The mixed layer is the part that feels the sunlight coming in, that is emitting infrared and evaporating as well. So what happens? So this guy warms up, and if it warms up, then you're increasing Ts. And if you're increasing Ts, then in a basically one-to-one fashion, according to this model, you're increasing Ta. And so you're going to be emitting more. So what I can do is basically think about linearizing this equation for the outgoing long-wave radiation. And so I get a perturbation to the basically I'm increasing the outgoing long-wave radiation by increasing the surface temperature here. And I'll write it as some constant beta times the perturbation temperature. So for those of you who are familiar with Taylor expansions, I'm just making the first order Taylor expansion for perturbation to the OLR. And so you can think of beta as being the derivative of outgoing long-wave radiation with respect to surface temperature. So if I warm up, I emit a little bit more radiation to space. But the other thing that happens is that if these guys warm up unevenly, then this guy's going to warm up first, and then it's going to start to warm up the deep ocean. So I'm also going to get a flux of energy that way. And again, I linearize it, and I just write it as proportional to the temperature, the perturbation temperature difference between them. So if they both warm up by 1 Kelvin, then I get no flux. But if this one warms and this one doesn't, then I get a flux downward. That's the model. So first, let's get a feel for these numbers. So let's estimate beta and gamma. So as I mentioned, we could use the simple climate model on the board to make an estimate of beta, right? That's the beautiful thing about simple models. So I'm calling this, let's call it RCE. So using our simple RCE model, right? Well, this is the derivative of OLR with respect to surface temperature, but I'll use the chain rule from calculus and write that as the derivative of OLR with respect to the emission temperature times the derivative of the emission temperature with respect to the surface temperature, right? But this is 4 sigma T emission cubed, and this is just 1, right, by this equation, or by this equation now. Right? So that gives me this, and then you can evaluate that, and this gives you something like 3.5 watts per meter squared per Kelvin. So for every Kelvin of surface warming, this is the additional amount of radiation at the top of the atmosphere that you see. All right, but what happens if you use, say, global climate model? So what is beta in the GCM? It's a lot smaller. It's about 1 watt per meter squared per Kelvin. And it turns out that gamma is pretty close to that too. So that's numbers we get from models. So this simple RCE model is getting us the right order of magnitude, but it's almost a factor of 4 off, right? So we're clearly missing some physics. So that's what tomorrow's lecture is about, in part. There's a discrepancy here. How do we understand it? So we'll learn more about that next time, and we'll improve our estimate by incorporating some additional physics. The point here is just to show you that this model can at least get you the right order of magnitude, right? Order 1 watt per meter squared per Kelvin. All right, great. So now we want to write down some equations. Let me move over here. So I want to write down equations for these two layers for the way their temperatures are going to evolve in time in response to this forcing. But to do that, I need to know their heat capacities. Right? The heat capacities are actually going to be the central thing. So to write that down, I need a few numbers. I need the density of water. So that's 1,000 kilograms per meter cubed. I need the specific heat of water. And that's about 4,000 joules per kilogram Kelvin. And then I need heights for these guys. And this is the key thing. So the fact that there are fast and slow components to global warming, as we'll see, comes from the fact that this guy, height of the mixed layer, is about 100 meters. But this guy, about 4,000 meters. So over an order of magnitude difference. That's the big difference between these two components. All right, so with those numbers in place, I can now write down our model. So first I'm going to write down an equation for the mixed layer. So I have the density times the heat capacity times the height. So this kind of gives me the total heat capacity of this whole layer, right? And then I have the time derivative of its temperature. And this equals all the forcings on it, right? This equals these arrows. So I know I've got my CO2 forcing coming in, but then in terms of outgoing arrows, I have this beta times the perturbation temperature. And I also have this gamma times the difference of the perturbation temperatures between these two guys. And the units of this are watts per meter squared. So hopefully that equation is easy enough to interpret. Right? You just have a change in temperature from a positive forcing, and then the response, which is negative, opposite the sign. So then we do the same thing for the deep ocean. So I have the same density, same heat capacity, but now I have the depth of the deep ocean. I have the deep ocean's temperature anomaly. And now I only have one arrow, which is the incoming flux from the mixed layer. So that's positive. All right. So now, so what can we do with this? So imagine that, let's just look at the mixed layer. Imagine that the deep ocean wasn't there, that its temperature wasn't changing. So imagine that this is 0, right? And actually imagine that what I want to do is I want to get a time scale for how quickly this guy responds. So imagine the system, but without any forcing. Forget about the forcing for the time being. Forget about the deep ocean. Then I only have terms. I just have dt prime is proportional to some constants times minus t prime. And so you can use that to get a time scale. And all it is these numbers divided by these sort of response coefficients. So characteristic time scale for the mixed layer. So I'll call this tau ml. So it's basically thermal inertia terms. Rho times c times the height divided by these response coefficients, beta plus gamma. And if you're not totally sure where this expression comes from, set this to 0, set this to 0. You get a simple differential equation which you can solve, and it has a time scale. The point about this whole model is that these came from GCMs admittedly. We don't, we have a first principles estimate for this that's too big, and we don't have any simple models for estimating this. So there is some GCM input to this. But the point is that just knowing these two numbers, I can now estimate the time scale over which the mixed layer responds. So you plug these numbers in, and you get something like 6 years. Right? Yes.
So if you're gonna ignore the deep ocean, shouldn't you set the temperature to be the same instead of setting it to 0?
So, guess what I'm saying is if you, I'm just trying to figure out a characteristic time scale. So, if I perturb the whole system, the response is a sort of sum of exponentials, each of which has a characteristic time scale.
Sure.
Right? So that's the complete solution. I'm trying to just isolate those two pieces. And so it turns out that the way to get the one of the time scales is just by ignoring the deep ocean. And just asking if I just perturb the mixed layer, if there's, without any deep ocean, what's the time scale on which it would respond?
But by setting it at 0, it's like you're radiating to 0 kelvins.
But you can just assume that there's no deep ocean, right? That the entire ocean surface is only 100 meters
But I
wide.
said you won't have the gamma term at all, that's what I'm saying.
I think I understand his concern.
Yeah.
It's that the primes are the deviations from the baseline
Oh,
temperature
okay,
pre-forcing. So he's saying set the perturbation of deep ocean to 0, assume it's not responding, rather than not there necessarily. Is that a fair?
Yes, thank you.
Yeah.
Okay, so now we'll do play the same game for this equation. We get a deep ocean time scale. Same density of water, same heat capacity, but now I have the depth of the deep ocean. And you'll notice that when I look at this equation, I don't have a beta term, right? Because the beta term is just how the mixed layer talks to the atmosphere. Deep ocean's not involved with that. So I just get these guys divided by gamma. And this is something like 500 years. So I have two. So this is global warming fast and slow. You have this fast time scale over which the mixed layer equilibrates. And then the slow time scale over which the deep ocean equilibrates. So what you can do then is ask about intermediate times. So consider some intermediate time scale, which is really what we have, right? Most of the carbon emissions that most of the CO2 we put in the atmosphere has been, I guess we usually say pre-industrial starts at 1850, but most of the emissions, the majority of them are since 1950. So it's really been 70 years, maybe. So that's right in this, it's right in between these two time scales. So we consider an intermediate time scale, such as the one we're experiencing right now. So it's some tau that's less than tau deep, but greater than tau mixed layer. Right? What do we find? Well, the mixed layer is going to be in equilibrium. It's had sufficient time to equilibrate to basically kind of the average forcing over this period. And it's been not enough time has passed for the deep ocean to really respond. So these are fair things to say on these on this intermediate time scale. The mixed layer has equilibrated, the deep ocean hasn't felt it yet. But now I can go back to my equations, right? So if I take these two qualities and I look at this guy, I set this to 0, and I set that to 0. And then I solve. And that's an equation that only has these three terms, and I can solve for the mixed layer temperature perturbation. So I get that the mixed layer temperature perturbation is the forcing divided by gamma plus beta. Now I can plug in numbers. So 3.5 watts per meter squared per Kelvin. I said that gamma and beta were each about 1. Sorry, watts per meter squared. I said that gamma and beta were each about 1 watt per meter squared per Kelvin. So this is 2 watts per meter squared per Kelvin. So this is about 1.8 Kelvin. is this how much global warming we've observed today? Probably about a degree. This is almost 2. Well, we haven't doubled, right? And in fact, there's another calculation you can do, very simple, using the fact that the forcing of due to CO2 is logarithmic in the concentration. But pre-industrial was 280. Right now we're about 400. The factor between them is roughly the square root of 2. And so that tells you that you should have about half the warming that you get at a doubling. That puts you right in the ballpark. Right? So this is all consistent. Now, this wasn't first principles, right? I got these numbers from GCS. Right? But the point is that it all hangs together. All right. A couple more things to say. So this is on the intermediate time scale. So this is describing where we're at now. On long time scales, right? So let's say we stopped changing the CO2 concentration in the atmosphere. We fixed it, say at 400 ppm, and then just waited, the 500 years, right? What will we find? Well, in this case, so this is tau greater than tau d. So let's go back to our equation. So now, both these guys are 0. We also know that these guys will be the same, so the temperature difference will be 0. They've come into equilibrium with each other, right? So this equation is just 0 equals 0. It's not telling us anything. But this equation, right, this guy's 0, this difference is 0, so the only two terms left are this. So that tells you on long time scales, T prime ml equals F2x over just beta. So instead of 3.5 divided by 2, this is 3.5 divided by 1, so this is something like 3.5 Kelvin. So these two numbers have names in the literature, in case that's helpful. Maybe you guys have heard of these. So this is essentially the transient climate response. And also known as the TCR. And this is the equilibrium climate sensitivity, also known as the ECS. And so sometimes you hear the phrase committed warming. This is what people are talking about, right? How much more warming will you get when you let the deep ocean equilibrate? And the reason the deep ocean's equilibration matters for the surface temperature is that on the intermediate time scale, right, this guy warms up, but the mixed layer has two places to which to export energy, right? It can send extra energy out to space, but it can also sequester some energy in the deep ocean. And so it can kind of come to a sort of temporary equilibrium at a smaller temperature, because it's got two places to dump its excess heat. But eventually, this deep ocean has had enough of that. It gets full, doesn't want any more. This difference goes to 0, and this reservoir is no longer available. And so now, this same forcing, there's only one place for it to go, this way, and the temperature must be correspondingly higher. And that's exactly, what I've said in words is exactly the difference between this expression, right, where the forcing has two places to go, gamma and beta, and dividing by a bigger number, and so I get a smaller temperature perturbation. Versus here on long time scales, there's only one place for the perturbation to go. Divide by a smaller number, and get by a bigger temperature perturbation. Yes?
I'm having a really hard time understanding why the heat in the surface ocean would want to go down to the deep ocean. It's stably stratified, it's very happy to be there. Anything that would be just going.
So I mean, there's an oceanic circulation, right?
Which is much slower.
Totally. That's right.
Which is much slower than the 500 years. I just can't imagine that the deep ocean is going to come to its equilibrium in 500 years.
Let's see.
So what is the mechanism of heat transport from the surface down?
That is a great question. And so I told you I didn't have a simple model for gamma. So I emailed someone at GFDL, and I said, do we have any simple models for gamma? Beta, I can estimate. And they said no. So it's a number you get from models, and the models have the whole deep ocean circulation in there. So you can think of all that physics, the entire ocean dynamics, as being wrapped up in gamma.
Okay.
And I wish there was a simple thing I could draw on the board to give you that 1 Walker meter squared per Kelvin. But to my knowledge, and I'm not an ocean expert, and all the ocean experts are actually at the Ocean Sciences Conference this week, so none of them are in the audience, which is a drag. And I only emailed one person, maybe I should have emailed more. But to my knowledge,
it has the physics in it. I mean,
it's all in there,
the
right?
circulation is all in there.
This came from a GCM, so it's in there. That was a good question. Ben?
Yeah, well, now getting out of the physics and into the biology, the time scale here is long enough that, going to the concept of commitment, you might expect enough carbon to be returned to vegetation and soil.
That's good. So Ben's pointing out, when I say that this is the committed warming, it's not really a fair statement, because this is assuming that the CO2 concentration stays fixed in the atmosphere. But we know that the ocean takes up carbon, the land takes up carbon. So there is a carbon cycle, which I have not modeled for you at all. So committed warming is in part talking about this, but then you also have to take into account the fact that CO2 concentrations, in sort of idealized model world, I'm doubling the CO2 concentration and just holding it fixed. It's not how the Earth system works. So thank you for that. Anna, and then Jane.
So the temperature you computed is the emission temperature? Does it correspond kind of to the left-hand side of the radiative?
What's
balance?
this?
Yeah.
This is the surface temperature.
The surface temperature. You don't need to go through the cycle of the convection and the...
You do, right? But I erased it. But what we had is that. So they're related in this one-to-one way. So that was part of the reason why I went through that model in the first place, is to say, look, the atmospheric temperatures and the surface temperatures are extremely tightly coupled. So a difference in one is a difference in the other. But it's a good question, and it doesn't hold everywhere across the Earth, right? In the Arctic regions, convection is not coupling the surface to the atmosphere, and so you cannot say that they move in lockstep. And in fact, they don't, and polar amplification is all tied up in this.
But you're assuming that the lapse rate is not changing because of the forcing?
I do, and that's not quite true, but it's a small perturbation space. Yep, Jane.
I'm missing something basic, so I don't understand why TD prime is 0 when you're at that intermediate time scale. I would think if the mixed layer is equilibrated, hasn't the deep ocean started to warm up a little bit?
No, you've dumped a lot of heat in there, but its heat capacity is so large that its temperature is not appreciably different.
Okay, so you have dumped heat in, but effectively the temperature is...
Exactly, because the heat capacity is large. Right, so over this whole 70 years, right? This guy's warmed up, heat is being fluxed down, but this reservoir is so big that on these timescales it's effectively infinite. So there's no temperature response, even though there's been heat sequestration.
But if you're close to 500 years...
Then you'll see it.
Okay, so we're saying it's like at 50...
Yeah, exactly. That's right. Yep. Yep. Rob.
Well, there are two kinds of questions that people ask. One is hold the concentration constant, which is what you can do.
Yes.
The other is stop emitting.
Yes.
Which is somehow the atmosphere scrubbed. Let's suppose you're going in that carbon, you just couldn't emitting 0.20 or something, stay without it, but now you're not doing it.
Okay.
The system does cool off. The atmosphere will, the concentration will drop.
If there's some mechanism for taking it up, either in the ocean or the land, or.
Right. But what am I saying? So I stopped the emissions. And people said, what happens after that?
Right.
Well, yes, I'm thinking primarily about carbon dioxide. So it does get scrubbed out.
Yes.
And that's carbon cycles.
Exactly.
It gets scrubbed out. Then I get a temperature decline, and that's a different calculation, but you can't do it until you have carbon cycle and fuel line.
Exactly. It's a different calculation. You have to have some model for the carbon cycle.
But you could do that, and that would be interesting.
Yes, agreed. And you and I have talked about how you get these interesting results when you include the carbon cycle, that the committed warming is a function just of the cumulative emissions, and that's not obvious.
Does that jump out of that result? That would be really important.
It would be great, and I've seen some attempts at a simple model, but I haven't really delved into it. But that would be a great next step, is to include the carbon cycle, and that would address Ben's question as well.
Yes.
Yeah.
So, and maybe this is getting off point, but going back to this gamma and the time scale.
Yeah.
So it's definitely it's not the sinking branch of the circulation that is bringing warmth down, because that you have to increase. Warming the deep is increasing potential energy. So what you need to do is do work on the ocean. So what is driving this is whatever does work on the ocean, so the winds. So I think there would be a way to estimate gamma by looking at the winds. I think that's so it's not the convective part, but it's rather it's the work done that allows you to increase the potential energy of the ocean.
Right. And somehow it's a function of this energy difference between the temperature difference between the two.
Yeah. So you grow the temperature difference, and if you have the same work going on it, then
yeah.
Yeah.
It'd be great to sit and write something down.
Yeah.
You know,
I don't think it's intractable.
Right. Okay. Good. Yeah. I mean, it definitely may be the case that no one has really wanted to do that. Right. Build a simple model for gamma. So it may not be that it's impossible or very difficult, just that no one has really tried. Go ahead.
This 100-meter mixed layer depth.
Yes.
Is this based on annually ocean mixed layer depth, or and also
As opposed to like some seasonally resolved, or
well, I guess I'm just thinking.
I mean, probably.
I'm just thinking about how much the fact that like land has such a small heat capacity compared to ocean.
Good.
And ocean heat capacity varies so much throughout the year. Like,
Yeah.
how much does it deviate?
Yeah, good. Well, I mean, so since ocean is 2/3 of the land surface, right? The errors. So you're right, there are errors, and actually, the person from GFDL who I emailed, he sent me back. He was using numbers, but he used numbers where you average the depth of the global ocean, which you took into account. But you said, oh, land has 0 depth. And you get a different number, right? But it's not an order of magnitude different. It's like 2/3. It doesn't change any of the conclusions, but it might change some of the actual numbers. It's about 7 minutes past, so maybe we'll sort of officially end, so people who want to leave can leave. And then I'm happy to stick around and answer questions that are just up on the board and get through it. So thanks a lot.